Hello everyone. Thank you for being here and thanks the organizer that gave me this chance to share my ideas here. My name is Shima Moghtasedi and today I want to present my PhD symposium which is about the similarity between temporal trajectories and graphs. In this talk, first of all, we will see how we model our trajectories and how we measure the similarity between them. And then after, we will see some research questions, and I will shortly explain how we address these questions in an efficient way. So let's go through the modeling trajectories. Most of the works which they study the movement, constrained movement by a network, they consider the trajectories which they are already mapped into a spatial network. While there are some applications which the movement is not spatially or physically constrained by network. Considering this type of applications, we use the topology of the network with no spatial information to define our trajectories. Presenting the movement with this type actually can provide us low dimensional indexing challenges and also less overall size of data that it could be important for designing a model in some cases. In our work, each trajectory is a sequence of nodes on the graph with no special information. Here we can see exactly how we define our trajectories by an example. We have two objects. They start their movement through the nodes of the graph. As you can see, each trajectory of moving objects is a sequence of pairs. Each pair contains one node and the time interval spanned by the trajectory on the node. Having this type of trajectories, to study the similarity between them, we need to design a similarity function, a proper similarity function. And since these trajectories are with no special information, so Euclidean metric couldn't be appropriate for computing the distance between them, and we need to compute the shortest path distances. So any proposed similarity function for this type of trajectories must be fast enough. While the most of the proposed similarity functions, they are quadratic time, and those linear ones, they only work for the trajectories with the same lengths. That it could be a big limitation. Moreover, involving the temporal aspect of trajectories into the definition of similarity function, the most of the proposed ones, they are a linear combination of spatial and temporal distances, and they control the relative importance of these two distances with the parameter. That sometimes finding a right value for this parameter would be difficult. Moreover, this type of functions can impose some unnecessary computations. So in our work, we proposed a linear time function that is able to compute the proximity between two trajectories with any arbitrary lengths, taking into account the structural and temporal aspect of trajectories in only one single function. This is a formal definition of our similarity function that intuitively this function for a given query trajectory Q and target trajectory capital T in a given time interval in an exponential function is assigning a larger contribution to those part of target trajectory which is close to the query and less contribution to the farther part of trajectories with respect to the query. So now we have a good metric to measure the similarity between trajectories, and we are ready to face with our first research question. For a given trajectory dataset and the query trajectory, which is a sequence of nodes, each node is assigned to a time interval, we aim at finding k trajectories with maximum similarity scores. For processing this type of queries, first of all, we need to retrieve most relevant trajectories with respect to the query in an efficient way. So we need to manage our trajectories in an efficient structure. Facing with the structural temporal trajectories, if we use the existing existing structure, indexing structure could be either inefficient or infeasible, since the most of the proposed special indexing are based on the artery, which is not applicable on trajectories with no spatial information, and the temporal indexing structures are based on the B tree, which could be inefficient when we are facing with time intervals. So we built our neighborhood trajectory indexing structure to manage our structural temporal trajectories by storing interval trees, assigning to each node of the graph, maintaining the time intervals spent by trajectories on the node of the graph or its neighbors. So as you can see, we have interval tree for each node of the graph. This is a general schema of our structure that we want to use it to process our queries. Due to the lack of competitors, as there are no linear time similarities for trajectories on graphs with no spatial information, so we design a baseline algorithm with respect to the general idea in the literature for treating this type of queries. That our baseline algorithm for a given query start to move through the nodes of the query trajectory, searching through the interval trees assigned to each query node, and finds the most relevant trajectories in a candidate set. Then the baseline algorithm computes the similarity score for each discovered trajectories with respect to the query, and then after reports the k-ones with maximum similarity score. And in our work, we aim at accelerating this process by proposing an approximate approach, and we call it shrinking technique. The basic idea here of shrinking approach is as follows. Suppose that this is a trajectory. In this approach, we want to present a sequence of node of the trajectory with a single node which is close to all of them. So we use the Voronoi diagram and graphs and partition our graph into disjoint groups of nodes. Each group has one center node. And then after we pre-compute the distances between Voronoi centers in a linear time, that in comparison with this quadratic time in a state of the art, it could be a significant achievement. And we will use these pre-computed distances to accelerate our query processing. As the next step, we want to use these Voronoi centers to compress our trajectories. So we represent each trajectory in dataset with the Voronoi centers as the shrunk trajectory. So in this way we are compressing our trajectories, or actually we are representing, or we can say that with a less number of nodes. So facing with shrunk trajectories, we need to modify our indexing structure to support this type of trajectories. So by adjusting our neighborhood trajectory indexing, we build a new Voronoi trajectory indexing, and we will use it in our query processing when for a given query trajectory we shrink the query firstly, and then by searching through the indexing structure we find a candidate set containing most relevant trajectories with respect to the shrunk query trajectory. And in both in two variants we produce one one estimated output set. In the first one, it's HQ, just we shrink our query trajectory and we estimate the output set by computing the similarity score for each discovered candidate trajectory and the shrunk query. So in this variant of the algorithm, we are reducing the number of shortest path distance computations, and consecutively we are reducing the time needed to find the solution for our query. And in the second variant, as HQT, we shrink both target trajectory and query trajectory. I mean, we estimate the similarity score. We estimate the output set by computing the similarity score for each shrunk candidate trajectory and shrunk query. In these variants, we are using the pre-computed distances because we just facing with Voronoi centers. We are working only with Voronoi centers, so we can use the pre-computed distances here and to be faster for answering our queries. To evaluate our strategy, we conduct several experiments on 3 real data sets. The trajectories over the network, over the Facebook network, the trajectory of taxi drivers in Milan, and the trajectory of tourists in Rome. That lack of space and time, I just present some part of our results here, just maybe most important ones. That one of them is time needed for query processing by each variance of algorithm in comparison with the baseline algorithm. And as we can see, our approximate approach can outperform the baseline, whilst our SHQT variance of the algorithm outperforms SHQ and the baseline algorithm significantly. Because in this variant we are using pre-computed distances. Another criteria that we need to measure is the quality of the produce results. Suppose that we have 2 output set. One is exact output set and the second one is estimated output set. We have 2 metrics here. SR ratio that computes the summation over the similarity score of trajectories in the exact output over the summation of similarity scores of trajectories in estimated output, and intersection ratio, which shows the common number of trajectories in both output set over the value of k. And in these 2 plots we show the values of intersection ratio and SSR ratio for different values of k's and k, and we can see that these values are always almost close to 1. That these plots can confirms the effectiveness of the proposed approach. So in the next step, we want to use the similarity between trajectories to solve one of the most important problems in tourism application, which is predicting the next movement for a given tourist. I shortly explain the idea here. Suppose that we have a set of point of interest in a city and a set of users, and for each user we have its trajectory in the city, which is defined as I already mentioned. And so for a given trajectory, we would like to predict the red point in this figure. So how we want to address this problem? First of all, we make a trajectory graph by each trajectory in dataset, and for a given query trajectory over the graph, we want to predict the red point by looking at the green point. That green point is assigned to a time interval. So by considering this query trajectory, we can find the most similar trajectory with respect to the query in this time interval, which is assigned to the green point, and the next movement of the most similar trajectory will be reported as the red point. This is a general idea of our strategy. That lack of time and space, I don't want to go through the details of our strategy, but to evaluate our method, we conduct a comprehensive evaluation over the 3 real data set of trajectories of tourists in 3 cities in Italy. One is Pisa, Florence, and Rome. And we compare our results with with the well-known machine learning based technique, as well as with the popular baseline. In particular, given a trajectory set, any such machine learning based technique needs to exploit a set of useful features, which it could be challenging. So in our work, we propose a graph based method for predicting the next movement of tourists without using machine learning based techniques. And we evaluated our strategy by over several experiments, but here I just present the most important one, the accuracy and the precision of our prediction model in comparison with our competitors. And as we can see here, our method can provide at least 2x more accurate results than the competitors in terms of the success at sign 1, that is the percentage of time, the number of time that we could find the right point of interest for a query, for a given query trajectory, which is a significant achievement. So yes, and in the future, the efficiency of the proposed algorithm would be better if a searching process through the indexing structure reports only distinct trajectories. So a problem that can arise here, it could be as follows: for a given trajectory set over the graph and a given single node or a set of nodes in a time interval, we aim at finding distinct trajectories traversed through the node, one single node, or a set of nodes in a given time interval efficiently. This could be a query that we want to work on this in future. And also we apply our strategy in tourism application, which the quality of the proposed methods could be better by applying an exact solution. And we want to use the time duration that each trajectory is close to the query trajectory to eliminate unnecessary trajectories, and then consecutively we are avoiding of unnecessary computations, and then we can reduce the time needed for query processing, and we can be better in our prediction. So we want to find an exact solution for our problem, and moreover, we would like to conduct a case study for validation of our model in other applications, like real-time detection of trajectories of people, news, events, and virus outbreaks. And here there is a bunch of references that I use for this presentation. Thank you for your attention, and I appreciate any idea and comments.